Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we will discuss about the AISC requirements for connection in case of tension member, then limitation for the slenderness ratio in case of tension member. Then we will go for design procedure for tension member, and finally we will solve one or two design examples for tension members. So first of all, requirements for connection. The minimum spacing of bolts or rivets. The minimum spacing of bolts or rivets should be more than 2.67 dB. So the spacing should be more than 2.67 times diameter of this bolt. And the clear spacing between these holes should be at least D. So it should be greater than D, and this pitch should be greater than 2.67 times diameter of the bolt. And the preferable spacing of the bolts is 3 times diameter. So this preferable value of pitch is 3 times diameter of bolt. Okay, next is minimum edge distance, the distance from the center line of the hole up to the edge. So this edge distance, it should be either according to this table. So for different diameter of bolts, the corresponding value for the edge distance is given in AISC code. So for example, for 20 mm dia bolts, the edge distance, the minimum edge distance should be 26 mm. Or otherwise, we can keep this edge distance more than 1.5 times diameter of the bolt. Okay, next is limitation on maximum edge distance. So the maximum edge distance should be less than 12 times thickness of the connected part. 12 times thickness of the connected parts under consideration, and shall not exceed 150, or it should be 150 millimeters. So lesser of 12 times the thickness of the plate or the thickness of the connected member, or the value 150 millimeter. So maximum edge distance cannot be more than 150 millimeter. So the next is maximum spacing or the maximum pitch of the bolt. So the maximum spacing of the bolts, it is decided based on the environmental condition. So if the member is subjected to corrosion, so then this spacing should not exceed 24 times the thickness of the thinner part, or 300 millimeters. So it means this should be, it should be less than 24 times thickness, or 300 millimeters. Similarly, for members which are subjected to corrosion and they are unpainted, so in that case this pitch should be less than 14 times thickness, or 180 millimeter. So 14 times thickness, or 180 millimeter. So these are the limitation on maximum and minimum edge distance, as well as maximum and minimum spacing of the bolt. Okay, next is what should be the minimum width of the connected leg. What should be its width? So its width is based on these factors. So first is transverse edge distance. So the distance from this edge up to the center of the bolt, so which we have studied in the previous slide, which should be more than 1.5 diameter of the bolt. So we should consider this transverse edge distance 1.5 times diameter of bolt. Then the clearance between this bolt up to the head of the bolt in the transverse leg. So the clearance to the bolt head on the other leg side from center of the bolt. So this distance from here up to here, so this should be equal to D times D plus 6. So diameter of bolt plus 6 millimeter. Then the thickness of this transverse leg, or the perpendicular leg, so plus the dimension of this bolt head, which is 0.75 times diameter plus 2 millimeter extra. So if we simplify this, so it will become 3.25 diameter of bolt plus 18 millimeter. So this is the case when the bolts are present on both the legs. So in that case we will consider this expression, and if the bolt is only on one leg, so then we can consider this expression. So by using these two expressions we can calculate the minimum length or minimum dimension of the connected leg, B minimum. Okay, for 2 or 3 meter long members, we can estimate this width of the connected member by L over 40. So L is the span of the member divided by 40. It will give us the dimension this much, minimum dimension that need to be connected with the other member. Okay, next is slenderness ratio requirement for tension members. So tension members are unlikely to be affected by their stiffness or by their slenderness ratio. It is recommended to limit the maximum slenderness ratio for all tension members except rods to less than 300. So the slenderness ratio should be less than 300 in case of tension members, and this limitation is actually used to avoid or to prevent the extra sagging or vibration due to wind. So if we have a long member, so it will sag under its own weight. So to avoid this sagging, we need to limit its slenderness ratio, or otherwise we need to limit its length, or if we cannot reduce its length, then we need to enlarge the section. And similarly, to reduce the vibration because of wind, so if the member is too long or it is too slender, so it will vibrate because of the wind pressure. So we need to avoid these two cases. So that's why we limit this slenderness ratio up to 300 millimeter. So up to 300. Okay, next is built-up section. So when the hot rolled shapes are unable to resist the applied load, then it can be combined to form a built-up section. So for example, if a single channel section is unable to resist the applied load, then we can combine two channel section to form a built-up section. So in case of built-up section, we can use lacing, we can use perforated cover plates or tie plates to connect these two parts. So this is the lacing. We can use this lacing to connect these two parts or two shapes to form a build-up section, or we can use this perforated plate. So we have connected this plate with the sections. Here we have 4 angle sections, and to connect those 4 angle sections we have provided this perforated plate. Or otherwise we can use this tie plates or end battens or intermediate battens to connect these two shapes, to connect these two channels to make a built-up section. So the spacing of these connecting members should be decided such that the slenderness ratio of the individual member should be less than 300. So the slenderness ratio of each component should be less than 300. Okay, next is design procedure. So to design, first of all, we need to know about the applied loads that we can get from the analysis. So once we have the applied load, dead load, live load, and wind load, and we also have the dimension of the member, then the next step is to calculate the factored value. So if we are using LRFD design method, so then we need to convert them into factored loads. Okay, so once we have the factored load, then the next step is to calculate the required area, or we need to select the trial section. So to select the trial section, we can estimate the area which is required to resist the applied load. So for that, we will again go to the basic equation of the limit state. For example, for tension yielding, we have Tn is equal to phi Fy Ag, and we know the design equation that Tu should be less than phi Tn. So applied load should be less than design capacity. So we know the applied loads. TU, and this phi Tn is equal to phi Fy Ag. So if we rearrange this equation for this Ag, so we will get Ag is equal to Tu over phi Fy. So by using this equation, we can estimate the grass area which is required for the member to resist the applied load. So here Tu is the factor load, so which we already know. Fy is the yield strength of the steel. If it is a 36 steel, then it will be 250. So this is the case for tension yielding, and if we are considering the case of tension rupture, so in that case the equation will become like this. So in case of tension rupture, our equation is Tu should be less than phi Tn. So Tu should be less than equal to phi, which is 0.75, and Tu is Tn is equal to Fu time Ae, or we can write it phi Fu time, instead of Ae we can write U and net area. And if I write this net area, or if I say that the ratio of net area and the grass area is equal to R, so A net over Ag, so then I can write that this net area is equal to R time Ag. So here I will replace this An with the R time Ag. It should be greater than Tu, or Tu should be less than this one or equal to this one. So if we equate this to equation and rearrange, then Ag will become Tu over phi Fu, U and R. So here U is reduction factor or shear lag factor, and R is the ratio of net area over grass area. So we can estimate the grass area required to resist the tension rupture or to avoid the tension rupture failure. So from these two equations, we can estimate the grass area for the required section. So here we have these two equations, this one and this one. So here we will input this Tu in kilonewton, then we need to multiply it with 1000, and phi is 0.9 in case of tension yielding, and in case of tension rupture it is 0.75. And U and R, U is the shear lag factor and R is the ratio of An over Ag. So initially we don't have the detail of the connection, so we can assume any reasonable value for U. So for example, we can assume its value 0.85. So normally this value is good, it is not too high and not too less, so we can assume this value. Similarly for R, we can assume the value again 0.85, mean the ratio of net area to grass area is 0.85. So it is the assumption at the initial stage. So at the later stage we can check the actual value of U and R when we have selected the connection and we have decided the connection details. So this step is to estimate or to calculate the required area. So once we have required area based on the applied load and the material strength, then we also need to find the minimum width of our minimum connected leg width. So we have already seen we can approximate this value by L over 40 if the member is 2 to 3 meter, or we can calculate this by 3.25 diameter of bolt plus 18, or we can estimate by 2.5 times diameter of bolt plus 16. This is when only one leg is connected, and this is when both the legs have bolts. Okay. So initially, if we don't know the diameter of bolts, so we can assume that the diameter of rivet or bolt is 15 millimeter. So initially we can assume its value 15 millimeter. Okay, now we have the required area, minimum width. So we need to select the trial section. So the trial section will be selected based on the 4 criteria. The first criteria is selected area should be greater than required area. So the section that we will select, it should have larger area than that of required area that we have calculated based on the previous two equations. And the section should be of minimum width. So we can find many sections with the area greater than this required. So we need to select a section which have least weight, and least are the smaller size. So smaller size as well as the least weight, minimum weight. And the connected leg width should be greater than minimum. So the width of that section of the connected leg should be more than this B minimum. For example, if we are considering this angle section, so the length of the leg should be more than this B minimum. And the compatibility of connection with other member is to be provided. So we need to keep in mind that we have to connect this member with the other member. So based on the requirement of connection, we need to select the shape. Either we can go for angle, C or W. So that will be decided based on the connection requirements, that it should be compatible with the other members. Okay, so once we have selected the trial section, so then we will perform the capacity checks to see whether our selected section is safe under the application of loads. So find actual value of U and AN if rivet pattern and diameter of rivets are known from the connection design. Okay, so next comes the capacity analysis. So we will use LRFD design method to calculate its capacity corresponding to yielding of gross section and fracture in the net section. So in this video, I will not cover the ASD method. So the approach is same in case of ASD, only the difference is we apply the factor of safety on strength instead of loads, and the factor of safety are different from the LRFD method. Okay, after calculating its strength, we need to compare it with the applied load. So if it is more than the applied load, then it is okay. Then we need to check the slenderness ratio limit. If the slenderness ratio is L over R minimum is greater than, is less than 300, then it is okay. And we also need to check for the fatigue strength as well as the design of lacing. But we will not cover these topics in this chapter. We will cover these at the later stages. For example, the design of lacing we will cover in the next chapter, design of compression members. Okay, we also need to design for the end tie. So if we have a C section connected like this, so in plane, so there will be like this. So we need to use end tie plates to connect this. And the length of the end tie plate should be 2 by 3 of S. And S might be if we have a welded connection at the ends. For example, we have welded the plate over here at these toes. So in that case, the length will be the distance between the welds. And if we are using bolts, so the distance between these bolt line will be S. So the length of this tie should be 2 by 3 of S. And the minimum thickness of this end tie plate should be S over 50. So this will be further discussed in case of compression members when we will study about the design of lacing. Okay, so after that we need to design the connection. So this will be covered in the last chapter. And finally we need to check for the block shear. So once we have the connection detail, then we can check for the block shear, and the block shear strength should be more than that of the strength corresponding to tensile yielding and tensile rupture. So at the end, if any of the criteria is not fulfilled, then we need to revise our section. Either we need to go for the larger depth or we need to go for the heavier section. So depending upon the situation, we need to revise our section. Okay, next is a example related to capacity analysis. So in this example, we will find out the capacity of a double channel section. So it is stated that calculate the factor load capacity of a double channel section member of A36 steel according to AISC LRFD specification. The member is 5 meter long. So steel is A36. It means Fy is 250 and Fu is 400 megapascal. Length of the member is 5 meter. We have two C's 200 by 20.5. So 200 is the depth and 20.5 is the weight per unit length. With flanges turned out, it means the configuration is like this. And the clear gap of 100 millimeters. So the gap between these two shapes is 100 millimeter. Assume that there are two 15 millimeter rivets for each channel at any cross section. So we have one fastener over here, one fastener over here. So two fastener in each channel, so one in each flange. So at any section, in case of built-up section, we will have 4 fasteners, and if we talk about only one channel, so we will have 2 fastener or 2 holes at any point or at any section. Okay. So assume that the next is the information given, because the complete detail of connection is not given. So it is given over here that assume U is equal to, or the shear lag factor is equal to 0.8. Okay, so we know this information. So the next information we can get about this channel section C200 by 20.5. So we can go into the LRFD manual, and corresponding to this section we can select the different properties. For example, it is this section 200 by 20.5. So we can select its area from here. So depth is 203 millimeter. Flange thickness that we need, it will be 59 millimeter. We also need thickness of flange, which is 9.5 millimeter. Similarly, we need this X value. X is mean if we have this flange, so distance from centroid up to this, the connection plane. So we need this value X, and we also need this second moment of area along x-axis and second moment of area along y-axis. So we need this information, so we can copy this information over here. Okay. So next comes, once we have selected all this information, next comes the capacity analysis. So we need to find its capacity corresponding to tension yielding and tension rupture. So if we talk about the tension yielding, phi Tn corresponding to tension yielding, so it is equal to, actually phi Tn is equal to 0.9 times Fy times Ag. So 0.9 times Fy is 250 and Ag is gross area of the section. So for single channel section we have the area 2610 millimeter square. So at any section we have a double section, so in that case its area will become twice. So 2 times 2610. So it will give us this phi Tn. Similarly, if we want to calculate the phi Tn corresponding to rupture, so we can calculate. So here we have calculated for yielding 0.9252 times 26, and for rupture it is phi T, Fu, U and An. So for this we need net area. So net area, obviously we have 2 rivets or 2 bolts in the flanges of each channel section. So the net area will be, A net will be equal to actually n times d plus 3 into t. So for one flange or for one channel section it is n is 2 and d is given 15 millimeter plus 3 and the thickness is 9.9. So from here we can calculate the net area for one section or for one C, and as we have 2 C's at any cross section, so in that case we need to multiply this with 2 to get the net area of the built up section. So it has been calculated over here. So An is equal to Ag minus n times d plus 3 into thickness of flange, because here the flange is connected, so we will use the thickness of flange. So this 2 is because we are using double angle section, then this much is the net area for single section. So the net area of the built up section comes out to be 4507.2 millimeters square. So we need to substitute over here. So 0.75 FU and this shear lag factor which is given 0.8 and then this net area. So from here we can get this capacity 1081.7 kilonewton corresponding to tension rupture. So now we need to compare these two values. So the lesser of these two will be considered as the governing value. So the lesser one is 1081.7 kilonewton corresponding to tension rupture. So this will be the design capacity. So now we need to check the other limitations. For example, the slenderness ratio, we also need to check for fatigue, we also need to check for block shear, but here the connection detail is not given, so we cannot check the block shear, so we can only check the slenderness limit. Okay, to check the slenderness limit, so it should be L over R minimum should be less than 300 millimeter, and if we see this R is equal to square root I over A. So, and R should be minimum. And for built up section, this I is equal to I of the section in, for example, in y direction plus AD square. So by using this expression, parallel axis theorem, we can find the I value, then substitute over here, we can get the radius of gyration, and then finally we can get the slenderness limit. Okay, if I talk about the second moment of area of the built up section, so in case of built up section, it will be calculated like this. So we have channel section like this, and we have a spacing of 100 millimeter over here, and we know the distance from this centroid up to this, which is x, which we can select from the table. And similarly, if we see the centroid of this section will be lie somewhat over here. So if we want to calculate the Ix value, so we need to consider this axis, and if we want to calculate Iy, so then we need to consider this vertical axis. And this section will have the minimum second moment of area corresponding to Iy, because in case of Ix, the more material is lying away from the neutral axis or from the centroid, so in that case the second moment of area about x-axis will be larger as compared to Iy. So the governing or the minimum second moment of area will be corresponding to Iy, and it will give R minimum value. So to calculate the Iy, we need to use this formula I y of built up section, or we can say Iyy is equal to Iy mean second moment of area of this section, single channel section, plus AD square. And this value we can select from the table as we have seen earlier, and we can also get the area of this single channel section from the table, which is 2610, and corresponding this D, so this D distance is from this centroid up to this new axis, so which is 40, mean x plus half of this 100 millimeters. So D will be equal to 40 plus 50. So when we will substitute this D values, we can get this Iy of the built up section. So here it has been calculated Iy about the individual centroid, which is given 63.7 times 10 raised to power 4 millimeter power 4. We can select this from the table, and the x value we can also select from the table. Then for the built up section, so I, y plus a and d square. So this is for one section, mean for one C to convert about this axis, and for the other C we can use the same approach, or we can multiply with the factor 2. So we will get this second moment of area of the built up section about the y axis. So from here we can calculate Ry, Iy over area. So here we will use the area of built up section. So 2 times 2610. So the Ry value of built up section is 65.88 millimeter. So R minimum is equal to Ry. So we can also calculate Rx, and then we can compare Rx and Ry and then select the minimum value. So here we have assumed that this section is stronger or this axis is stronger, so the failure or the bending will be along this y-axis, and this is the weaker axis, so we only calculated for Ry. So once we have our minimum value, so length divided by R, we will get the slenderness ratio and it should be less than 300, so it is okay. Okay, finally we need to check for the width of the connection member, connected leg. So here this one will be the connected leg. The width of flange. So we need to select the width of flange so that we can select from the table, which is 59 millimeter, and we need to compare it with the minimum value. And minimum value here only flange is connected, no bolt in the web, so we can use this formula 2.5 times diameter of bolt plus 16 to calculate the B minimum. So 2.5 diameter plus 16, so it is 53, but the width of flange is 59, so it means the length of this connected member is okay. So this limitation is also okay. Then we need to check for the fatigue failure. So here we are not given with the loading cycle, so we cannot check this. So finally our tensile capacity will be based on the tension rupture that we have selected earlier. So this is the procedure how we can check the capacity of a section. So we need to investigate its capacity corresponding to tension yielding and tension rupture, and then we need to perform different checks. For example, we need to check the limitation of slenderness ratio, we need to check for the minimum width of the connected leg, we also need to check for the fatigue failure and block shear. So we cannot check the block shear until we have the detail of connection.